Hello guys, welcome back to Maison African Motives, still on industrial electronics and one in this platform. We have the question paper which was written in April 2023 that we are going to work on as our revision in this case so that we can see how we're supposed to attempt these typical questions. So we are given first our instructions and information, especially guys to take note of the value of pi, which is 3,142, and approximate all final answers accurately to 3 decimal places. That's what you're given in this case. All right. So let's check what you're given. On question number 1, we are given that various options are given as possible answers to the following questions that we are given in this case. So out of these various options, choose the answer and write only the letter A to D next to the question number. All right. So here we are given 1.11. An atom is electrically neutral because why is it electrically neutral? It is because the number of protons and the number of electrons are equal. That is why it is electrically neutral. They are equal. So our answer is supposed to be a B. The particles found in the nucleus. Which particles do we have in the nucleus? Remember, in the nucleus, we've got protons and neutrons, and this is on A. So your answer was supposed to be A in this case. 1.3, when atoms combine to share one other's valence electrons, which is we're talking about outer shell, and or a special dash bond is formed. Which bond is formed in this case? That's a covalent bond. So our answer was supposed to be a D in this case. The valence shell of an electron is that is the one that I was talking about here, the valence, that is the outer most shell. So that is going to be A. So our answer in this case was supposed to be A, the outermost shell. 1.15, which one of the following is not a fundamental particle of an atom? Remember, on an atom, it is made up of electrons, it is made up of protons, it is made up of the neutron. So the alpha particle, this one is the one that is not, remember, is not. So that is the alpha particle. 1.16, which one of the following is not an advantage of secondary cells? We have got, in this case, produces high current. It's actually an advantage. Slow charge rate recommended, that's a disadvantage. So this one is supposed to be our answer. Rechargeable, it's an advantage. Long life expectancy, it's an advantage. All right, so the answer was supposed to be B. Then on 1.7, capacitance is measured in, what is the unit? The units for capacitance is farads. So the farads, that is the unit for capacitance. The ohms is for resistance, this one. So okay. 1.18, which one of the following is not a factor that determines the resistance? All right, we can take this from the formula for resistance. Remember that resistance is equivalent to rho L over the area. That is the resistivity times the length over the area. So that means we need length, we need resistivity, we need cross-sectional area. But what about inductance? We do not need inductance. So inductance is not needed. It's not a factor. So inductance is not a factor. All right. 1.19, the type of a waveform where current is in one direction of constant magnitude. Our current is direct, like one magnitude. We are having same magnitude throughout a constant magnitude. So that's a direct current in that case. So we have got a B in this case. All right, 1.110, an instrument used to measure relative density in liquids. Which instrument is it? That's a hygrometer. All right, a hygrometer is used to measure relative density. All right, then on the other part of the question, which is 1.2, so that was question 1.1 and so forth. On 1.2, we are now given that complete the following paragraph by choosing word or words from the list below. Write only the answer next to the question from 1.1 1 up to 1.110 in the answer book. Okay. So we are given our answers. In this case, these are the answers. So we've got this statement that you're supposed to complete in this case. Doping is the process of adding impurities to an what where are we going to add these impurities? We are adding to an intrinsic semiconductor in this case. So this was supposed to be intrinsic semiconductor. All right, material and doped material is known as the doped material is an extrinsic semiconductor. So this is extrinsic here. So this is extrinsic semiconductor. All right, material doping, donor doping is a process. We're now talking about donor doping is a process of generating free, what is it that we are going to generate? So that is free electrons. So here, these are free electrons in the crystal lattice structure by introducing what impurity? Okay, so this by introducing a pentavalent impurity. So the pentavalent here is 1.24. All right. That is a material with valence electrons, with what? 5 valence electrons. An example of such material is, what is an example from this? That you've got 5 valence electrons. That is a phosphorus in this case. So the example of such material is phosphorus in this case. Acceptor doping, that is the acceptor doping, is a process of introducing, what are we introducing this time? We are introducing a hole in the crystal lattice structure by adding impurity atom. So it's a trivalent in this case, this one. So that's 1.28, which is a trivalent impurity atom. That is a material with how many valence electrons? 3 valence electrons. So this is supposed to be 3 valence electrons. An example of such material that has got 3 valence electrons is what? It's a boron this time. So this one is going to be a boron. All right. So that is what we're supposed to have in this case. You were supposed to answer according to the information that you're given in this case. All right. On question 2, we are given that we have got a series connected circuit that has got 3 resistors with values R1, R2, and R3 is unknown. The circuit is connected to 100-volt supply and a total resistance of 270 ohms. All right, so this is a circuit that you're given. So that's question 2. So we're given that this circuit is in series. All right, so we have got 3 resistors in series. So you can just have first resistor, the second resistor, the third resistor like this in series, then connected definitely to a certain supply. All right, like this. So this is what we just a sketch of the information. So we are given that the first resistor in this case is R1 83, R2 is 120. So we have got 83 and 120 in this case. So this is 83 ohms, 120 ohms. Then the third resistor, we do not know its resistance. All right, so this is our R1. This is our R2 in this case. And that is our R3, the one that we do not know its resistance. But we are given that the supply voltage is at 100 volts. Then the question is asking us in this case to calculate the value of the unknown, or to determine the resistance of the unknown resistor R3, given that the total resistance in this case is 270 ohms. So we are given the total resistance that it is 270 ohms. So if RT is 270 ohms, what about the value for R3? Remember, this is in series, and we know that in a series circuit, the total resistance is going to be the sum of the resistors in series. So we're going to add R1 plus R2 plus R3. So that is in series. So we can substitute what we are given in this case. We have the total resistance of 270. So that is 270 ohms is equivalent to R1, that is 83, our first resistor, plus R2, which is our second resistor of 120, plus R3, which is the unknown resistor. So we can solve this by solving the equation. All right, so by solving this equation, meaning to say we can add from the left hand side, from the right hand side here, we can combine these 283 plus 120, which is going to give us 203 plus R3. So we can transpose this to the left hand side so that we can subtract. This is going to be 270 minus 203, which is equal to R3. So if we subtract, that is going to give us 63. So if 63 is equal to R3, that means R3 is equivalent to 63 ohms. All right, so that was the resistance R3 in this case. That is the unknown resistor that we're given. Then the color coding of R3, if it has a tolerance of 5%. So you see, if you have this, if you have a wrong answer for R3, it's affecting this one also, because the R3 that you got your answer is the one that you're working from. So now we need its color coding given a tolerance of 5%. All right, so this is 2.12. So let's check what we have on R3. We remember we calculated the resistance. So 2.12. We got that R3 is equivalent to 63 ohms, and we are given a tolerance of 5% in this case. So that is plus or minus 5%. So remember, on your color coding, this is going to be the first digit, the second digit, then the multiplier in this case for us to obtain 63, it means we were multiplying by 10 to the exponent of what? Of a 0, which is equivalent to 1. 10 to the power of a 0. So in this case, our first digit is 6, which corresponds to which color? This 6, which is the first digit, which is a blue. So remember, 6, that's a blue. Then 3 is a digit again, which corresponds with orange. All right. Then on the multiplier, 10 to the power of 0, which is same as 1, is on black. The 0 there is on black, which is the first one. Then a tolerance of 5%, that is for gold. So these are the colors which were needed in this case, which is the color coding of R3s. Okay, so that was 2.12. Then let's move on to 2.13. 2.13, the total current through the circuit, and that's 2 marks. Remember that total current is taken from what? From the total resistance. We are given the total resistance of the circuit. We have got the total voltage. So that means we can calculate the total current, that is the total voltage over the total resistance. So our total current is going to be the total voltage of 100 over the total resistance of 270 ohms. So if we are to divide this, we are going to obtain our current, which is in amps. Remember that current is measured in amps. So you're going to obtain something like 0.3737 and so on, which is to 3 decimal places as per given instruction. It is going to be 0.370 amps. So that is what you're going to have as your total current, or just 0.37. All right. So in this case, we have the total current, but remember, this is a series circuit, guys. If we have got our total current, in this case, we are given a total current of 0.37 amps. This current in series is the same. It is going to affect R1, it is going to affect R2, it is going to affect R3. Same current throughout. That's in series. All right. So let's check the second question. The other question, that is on 2.14. We are now asked to calculate the voltage drop across each resistor, and that's 6 marks. So the voltage across each resistor, take note, we have each resistor here. We've got R1, we've got R2, we've got R3. And from what I was saying in a series circuit, the current is the same. So if we've got the same current, that means we are going to have the voltage drop of R1, the voltage drop under R2, the voltage drop under R3. Which is voltage is the product of current and resistance. So that means in this case, we are going to have V1 as the total current times R1 because current is the same. So that's 0.37 times R1, which is 83. So you're going to multiply 0.37 times 83, that's 30.71 volts. So you've got V1. We move on to the voltage drop across R2 in this case, which is going to be the total current times resistor R2. So that is our V2, which is going to be 120. Our total current in this case, that's 0.37. So we've got 0.37 times the total, the resistor R2, which is 120. So that is going to give us the voltage drop across this resistor. That's 44.4 volts. We move on to R3. Remember, we calculated R3 before and we got that we got our R3 as 63 ohms. So this resistor R3 is equivalent to 63 ohms. So that means we can calculate V3 in this case, or VR3, VR2, depending on the way that you are writing. So it's going to be total current times resistor R3, since current is the same in the series circuit. So 0.37 times the resistor R3, which is the one that we calculated before. So that is going to give us 23.31 volts in this case. All right. So that was our question 2.14. Let's check the other part of the question where we are given now to draw the circuit diagram. That is, draw a neat labeled diagram of the circuit. So that is a circuit diagram. So in this case, I already drawn this sketch of the diagram. So definitely this is how your diagram is going to be. So this is just a sketch, but make sure that you do it in a neater way. So that is your 2.2. You're just going to have this diagram. I already drawn it for calculation purposes so that you can see how we are obtaining our calculations. But now 2.2 needs you to draw this diagram. So if you have drawn a sketch, then you are supposed to redraw it again. So you're going to redraw this diagram as it is on your 2.2. All right, so that is it. You can obtain 5 marks from there. Then on question 3, we are now given that to draw the IEC circuit symbols for each of the following components. That is the first one, a potentiometer. So remember, a potentiometer is just a resistor that you are given, but only that we are going to have it this way with let's just say an arrow here pointing to this. So that becomes a potentiometer in this case. So you can even draw it as a normal resistor. Remember your normal resistor, then you can. But you are having these guys with your ruler. Please make sure that you draw something properly. Okay, in this case, I'm just showing you like a sketch. A preset inductor. So just from your normal inductor, remember your inductor, you're going to have something of this nature. Then for it to be a preset, you're going to have it this way. That's a preset inductor. All right, an echo inductor. That's a normal inductor that you're just used to, just a normal coils like this. That's an echo inductor. Then a transformer. So a transformer, you can have it in different ways depending with how you want to present it. You can even present it this way, a simple circuit like that. That's a transformer. Then an electrolytic capacitor. So this, we are supposed to show the polarities of this capacitor. So you can have it this way. That's something like this. So this can be our positive and this will be the negative. Okay, so that was just having the symbol for each. All right, as a part of a laboratory on question 3.2, you are given experiment on cells. Okay, you are given 1.5 cells with negligible internal resistance and a 10 ohm load resistance. So they've got a negligible internal, which means the internal resistance cannot affect us at all. Show by means of a neat labeled circuit diagram how to connect, take note, how to connect the circuit Using all these components, the ones that we are given, which is the 3 cells and the load resistor, to ensure that 1,5 volts is applied across the load resistor. How can we measure this voltage of 1,5, which is across each cell, to be the same voltage also across the load resistor? How is it possible? This can only be possible if the load resistor is in parallel to the what? With the 3 cells. Remember, in parallel, voltage is the same. So that's only the part that can give us a 1,5 volts on the load resistor. So this can only be if it is connected in parallel. So it's only by means of a parallel circuit. So you can have your load resistor here, so, and connect the those cells. Remember, these cells, they've got 1,5 volts each, and there are 3. So we are going to just connect them in parallel, so that we are going to have 1,5, 1,5 throughout in a parallel circuit. It's very, very possible. That's what we have. Voltage is the same. In a series circuit, it is the current which is the same. So here, guys, just pardon my diagram, but you're supposed to have something of this nature like this. Okay, so these are our 3 cells, each having 1,5 volts, 1,5 volts, 1,5 volts. So this 1,5 definitely is going to be measured across the resistor because it's in parallel with the resistor, which is our load resistor in this case of 10 ohms. So you're given a load resistor of 10 ohms. So the currents, they are different. Remember that your currents, they differ according to the supply. Say this one is going to branch, we are going to have a current flowing in this way, but the voltages are the same. So that is the only way for us to measure 1,5 volts across the load resistor here. That's the only way that we could have done to connect in a parallel. All right, list the 4 factors that determine the resistance of a material. If you saw previously, we had this question where I mentioned about the formula that you're going to use for the resistance of a material. Remember that the resistance of a material is given by the formula rho L over area, which is resistivity times length times area. So the factors which affect the resistance of this material is the resistivity. In this case, we have got resistivity. That's the resistivity in this case, which is the type of material. So we're actually referring to the type of what? The type of material. Okay, we have got the length in this case. So we have got the length of the material, or the length of conductor. Let's just say length of conductor in this case. We have got the cross-sectional area in this case, cross-sectional area. We have got the temperature, which is the ambient physical factors not given here, but also affects the resistance of a what? The resistance of a material. So these are the 4 factors that we have. All right, on 3.4, list 3 disadvantages of a digital multimeters. Okay, digital multimeters, they also have disadvantage. It's not only about, they also have okay, this advantage. This is advantages. All right, this is advantages. Sorry for that. So we have got advantages of digital multimeters. So they are actually, we have got so many. So here I've got some few. That is automatic output display, automatic output display. It's an advantage. Also, accuracy, the accuracy is high. So you've got high accuracy. It's very, very high. Okay. Then we have got high input impedance, high input impedance, high input impedance in this case. So any others, guys, let us mention on in the comment section so that it can help another one to add more questions. more points on advantages of what digital multimeters. All right. Differentiate between a positive temperature coefficient, which is PTC, and a negative temperature coefficient, which is the NTC of resistance. All right, so what's the difference between these two, the PTC and the NTC? Positive temperature coefficient, negative temperature coefficient. Okay, the difference is if we are dealing with the NTC, it reverses the issue of temperature. It reverses the NTC. The issue of that when temperature increases, the resistance decreases. So it opposes to say as temperature, all right, as temperature increases. So if your temperature is increasing, in this case, resistance decreases. So resistance in this case decreases. So that's what's happened with NTC. It opposes, which means as temperature decreases, resistance increases. All right. Then for the PTC, it is in parallel, which means as it increases, it increases. As it decreases, it decreases. So which means in this case, as temperature increases, so as temperature increases, that means at that condition, resistance also increases. So resistance increases also. So that is what we are going to have, or you can even try to do it graphically. But in this case, we can even just do it in theory like this. All right, so that is what you're given on question 3.5. On question 4, this fig below shows the circuit symbol of a popular electrical device. Which device is it? That is 4.11 named device. So that's a transformer. This one, we even talked about this before when we're having those symbols. So that's a transformer. Then 4.1, we are now asked to list 4 faults that may occur in the device, which means we are just asked to list the factors the faults of a transformer. What are the faults of a transformer? We have got overheating. So it's a fault that can happen on a transformer. We have got winding faults. All right. We have got winding faults in this case. All right. We have got open circuit. A transformer can have an open circuit. It can have core faults. All right, we can have core faults. In this case, we can have earth faults. So there are so many faults that can actually happen in a transformer. So just mention others, guys, so that it can help us in our revisions. All right, 4.13. If this device, which is this transformer, they are saying if we've got 100 turns in the primary of a transformer and 20 turns in the secondary, calculate the primary voltage if the secondary voltage is 3 volts. What are we given? All right, that's 4.13. We are given 100 turns in the primary. Okay, so let's just list our information. So that's 4.13. Okay, so we've got the turns in the primary, which is 100 turns in this case. Also the turns in the secondary, 20 turns in the secondary. So in the secondary, we've got 20 turns, which is number of turns in the secondary is 20. Then also we are given part of the information that to calculate its primary voltage. If the secondary voltage is 3 volts, which means we have the secondary voltage, which is Vs. All right. So in this case, we are given Vs being 3 volts. What about Vp, which is the primary voltage? All right. So remember from your turns ratio or from your transformer equation there that you can equate the ratio for number of turns. Np over Ns is equal to Vp over Vs, which is equal to Is over Ip. So in this case, we are referring to what we have, that is the number of turns and the voltage. So we can work with this. All right, so that is what you're going to do in this case. So we are going to solve for this. So taking our solution from Np over Ns is equal to Vp over Vs. Np, that is 100. So 100 over Ns, which is 20, is equivalent to Vp. That is the one that we are supposed to calculate over VS, we are given VS as 3 volts. So what is the value for VP? So by cross multiplication, we can calculate this value of VP. That is going to be 20 times VP. That's 20. VP is equal to 3 times 100, which is 300. So if we can divide by 20 both sides, that is going to give us the value of V, which is VP. So VP, the number of voltages that we have, voltage is 15 volts. That is the voltage in the primary side of the transformer that we are given. All right, so that was our question in this case, which we just used the ratios. If we are given current, you work with current. If you're given the tens, you work with the tens that you're given. All right, so that was your question 4.13, having a total of 4 marks. Okay, on question 4.2, we are now given to define each of the following terms. That is the Faraday's law and the Ohm's law. Right, this is actually a lot. Okay, let me just see if I can just write it aside here. All right, so that is 4.21. We are given the Faraday's law. All right, so that is Faraday's law in this case. So it states that the EMF, so the EMF is induced. So the EMF induced is directly proportional, all right, is directly proportional to the rate of change, to the rate. So that is to the rate of change, to the rate of change of flux. That is the rate of change of flux, linking the coil or circuit. So it's going to link the coil or the circuit. All right, so this is what we can have as our definition for the Faraday's law. All right, the other one, 4.22, that's the Ohm's law. All right, so this is actually 3 marks each, 2 times 3. This was a lot of marks. All right, anyways, we are supposed to know these laws, guys. Okay, so 4.22, we are given the Ohm's law in this case. So that is the Ohm's law. All right, so the Ohm's law, it states that the current flowing, so we have got the current flowing in a circuit, the current flowing in a circuit is directly proportional. That is directly proportional. So take note for this one, directly proportional to the applied voltage, to the applied voltage. So that is directly proportional to the applied voltage and inversely proportional to the resistance, and inversely, so that's in here, inversely. So take note, inversely proportional to resistance. Proportional. All right. So that is what you're going to have to resistance, to the resistance in this case. So we can just have this as our laws. So the Ohm's law, it states that the current flowing, take note, in a circuit is directly proportional to the applied voltage and inversely proportional to the resistance. All right, so that is what you are given in this case. All right, then on 4.3, we are now asked to calculate the peak-to-peak RMS value of an average value of AC voltage with a maximum of 180 volts in this, 180 volts. So we are given to calculate the peak-to-peak RMS value. So remember that that's 4.3. So 4.3. So here we have got a peak-to-peak value. So from the RMS value, remember we have got our RMS value, which is our maximum value, which is VRMS, that is 180 volts. So we know that our VRMS was equivalent to 1/2 square root of 2 times VPP like this. All right, which can be manipulated to calculate VP, which is peak-to-peak value. So our peak-to-peak value is going to be, if you cross multiply, this is going to be 2 square root of 2 times VRMS. So this 2 square root of 2 it can be given as 2, 8 to 8, 4 like that. Okay, so you can even use this value, or you can use 2 square root of 2. So that is how you calculate the peak-to-peak value, which is going to be 2 square root of 2 times V RMS of 180 volts. So this is going to give us 509. So you're going to obtain 509,117 volts. All right. So that is what we had in this case. Then on 4.3, name 2 most common faults that can occur in inductors. Okay, so inductors actually it's about the open circuit and short circuit, and also the issue of overheating. So you can have open circuit and short circuit there. All right. Question 5, indicate whether the following statements are true or false by writing only true or false next to the question number 5.11 up to 5.12 to the answer book. All right. Carbon composition resistors carry large currents. Is that so? No, carbon composition, they carry very small amount of current. So this is actually false. All right. Resistors limit the current flow in a circuit. That's very true. So this is true. Whenever you place a resistor, you are limiting or reducing like the amount of current flowing. You are limiting that current. Name 3 factors that affect the capacitance of a capacitor. All right. So on the capacitance of a capacitor, we remember that the capacitance of a capacitor is equivalent to EA over D like this. So we've got the dielectric, that is the area and the distance between the dielectric. Okay, so this is 5.3. All right, so 5.2, sorry. So we said we have got in this case for our factors, the cross-sectional area. So we've got cross-sectional area. All right. We have got the issue of the dielectric. All right. We have got our dielectric, or that is the type of dielectric that is being used, and the distance between plates, which is the D. So the D is the distance between plates. So if you know these formulas, it's important for you to know the formulas because you can take the factors from the formula. All right. So that is what you're given in this case. 5.3, we are now given that there are 2 capacitors, which is C1 and C2, with the values 15 microfarad, 35 microfarad respectively, are connected in series. Calculate the total capacitance. All right. So these are in series. Remember, guys, when capacitors are connected in series, they act as resistors in parallel. So they act as resistors in parallel. So they just oppose what you know under resistors. Series, they act as resistors in parallel. Remember, resistors in parallel, because you are used to resistors. That's product over sum. So meaning to say, to calculate the total capacitance, we're going to use 1 over CT, which is equal to 1 over C1 plus 1 over C2. We can use this formula, or we can just use product over sum because these are 2 capacitors. Remember, for resistors in parallel, if you've got 2 resistors, you can just use product over sum, R2 by R1 over R1 plus R2 product over sum. So it is the same also even for capacitors in series. If they are 2, you can use product over sum, which is C1 times C2 over C1 plus C2. So knowing that these capacitors, they are in microfarads, we are just going to use the 15 as it is, the 35 as it is, but your answer is going to be measured in microfarads. All right, so that is going to be 15 times C2, which is 35, over the sum of the resistors, 15 plus 35. So you can use this one, or you can use this formula. Still, you're going to have the same answers. So that means our CT is going to be 10 comma, so this is going to give us 10,5. So that's 10,5. But remember, the values here were in microfarads. So this answer is going to be also in microfarads. So that's our CT. All right, 5.32, the total charge of the combination if 60 volts is applied. Okay, so we have applied 60 volts, which means we now have the total voltage and the total capacitance in this case. So that's 5.32. So remember that charge, if you are to calculate charge, which is the total charge in this case, that's the total capacitance times the total voltage that you're given. So you're given a voltage of 60 volts, which is acting across, which is your total voltage. So that means total charge is going to be, so this was 5.32, yes, that total capacitance, which is 10,5 microfarads, that's times 10 to the power of minus 6, times the voltage of 60 volts. All right, so if you are to calculate this properly, your charge, which is Q2, is going to give you something like 0,00063 coulombs. Okay, so this is going to be coulombs like this. Or if you want, you can write this as, just to avoid the decimals, you can write this as 1, 2, 3, 4. So you can write as 6,3 times 10 to the exponent of minus 4 coulombs, just to make sure that you are starting with a whole number, or you can leave your answer like that. It's fine like that. Don't even waste much time. If you do not understand this in final exams, it is going to be tricky. You leave it like that. All right, so that was our question that we had. Let's check the other part of the question, which is, I think, the last part of the question, which is 5.4. We are now given to draw a neat labeled single stage NPN transistor amplifier in a common collector configured. Take note, common collector configuration, showing both the input and output waveforms, and that is 8 marks for that. All right, so let's see how you're going to draw this one. All right, so I'm just going to show you just a simple circuit, guys, just a simple one that you can use. So remember, that's an NPN transistor. So we are going to have on the input, there is going to be a capacitor here to the transistor. So you're going to have your transistor NPN. So that is the most important. You are supposed to show that's NPN going out like that. All right. So this is what you're going to have in this case. So that's our NPN transistor here. So we've got a capacitor here, then our resistors, the voltage divider, the ones that are going to divide the voltage here. So this is going to separate from the input. All right, so that is going to be like this. So you can have a resistor to the base like this. All right, so that means here, this is going to give us the input. All right, so here we are going to have our input. In this case, this is the input, which is a sine wave. So that's your V in, which is a sine wave. All right. The output part is going to be also a sine wave. So let's connect to the output. So this is going to be a capacitor also here. All right. Then we have another capacitor also on our output part here. This is the output part. All right, like this. All right, then I'm gonna just have it this way. Okay, I think it's clear. All right, let's extend some of this. Okay, so here we have got the input capacitor, the input resistors, which is the voltage divider, which is R1 and R2 here. Then we have got our RE. Then we have got our C1. All right, let's just save C1 and output, which is CO. Then this is where we have our V out in this case, which is a AC like that output. That is your waveform, the output waveform. Then this is plus VCC. All right, so yes, we can have it this way. Yes, that is a NPN. common collector configuration. Take note. So that was our question, guys. Question paper having a total of 100 marks. So for more, please make sure that you subscribe at Maison African Motives. And also don't forget, guys, to share our platform to your friends and colleagues, to share our videos to your friends and colleagues at school so that they also can revise with us as a family from Maison African Motives till we meet again.